All right, hello everyone. Welcome to another day where we try to make a full 3D game engine in Golang. So, continuing from last time, just one, see, we're building the I'm GUI integration, and I think we're basically done, at least for now. Don't think there's anything fancy we want. And we added a little bit of ambient light, so we can play with the ambient light affecting all objects, and we can have something really nice, right? You can play with the strength and whatnot. So we'll probably leave this for a while now. No more GUI for a bit. What I have been working on for some time, and we talked a bit about it in last streams, is assets importing. And the idea is we want to load a ton of assets, right? Different 3D models from different programs, like if you're using Blender, if you're using Maya or whatever else you're doing, there are just a lot of them, and they can get pretty complex, and some of them are closed source, so there aren't official documentation that's available on how to load them and use them. So for example, one of the most popular is FBX, and it's not an open format. And these things can contain animation and keyframes and lights and whatnot, multiple objects, and they can get very big. So we're not going to, I think at least for now, to be writing all of that code ourselves. Instead, we wanted to use a library that does this for us. And so the most popular thing it's called Open Asset Import Library, right? AssImp, but it's written in C++. And I've been spending the last 2 weeks, maybe, right, building this, building a wrapper for it in Go. And there is a complete version, basically, in Swig. So this is auto-generated, but I didn't like it. It's a ton of code, and we don't need all of that. And the interface is not very nice to use as a Go developer. So I started writing, and it's at a pretty good stage, but I made a handwritten wrapper for at least some the fundamental import features. So far we have mesh data, everything like UVs and vertices and whatnot being loaded correctly, materials, textures, error reporting, and all the enums that we need, all in kind of being Go native. Lights and cameras, I'm not sure if those would be important for us, because it's we're doing a real-time thing. So the camera will be in game, the lights will be in game. I'm not sure we'll need those. So I won't be focusing on them, but soon enough we will need animation. So that's one thing I should integrate. If someone would like to contribute to this, please go ahead. It's AssImp-go, employees/AssImp-go. It's open source, and I think today we'll be using it. So we'll integrate this into nMage, our game engine, and start being able to load everything we want. And then once we have normals and UVs and whatnot coming in, then we can start doing lighting, and we can start doing texturing and whatnot on complex models. And this is what we want. So so far I only did one change today, which is to go get this library. And so far it works on Windows. It should work everywhere else, but it's just that I haven't built the binaries for it. So if someone would like to contribute the binaries for macOS, like just building AssImp, the C++ project, and giving us static libraries to work with, then we could do that. Or I'll probably do it some later point, right? So I already got that. If you're doing it for the first time, might take a bit to load, because it's kind of large. AssImp is a large library. It does a lot. And now we zoom in here. So we have nMage, and we did our GUI stuff, inputs, and so on, right? For UI. So let's start focusing on imports. So last time not last time, but before, we got this obj file where it's specifying, I think, normals and the faces, the indices, and whatnot. And we wrote a small simple loader by hand. So for a start, I think let's try to use AssImp and kind of replace the way we load it. Instead of this function, we'll be loading it through AssImp. So we won't have this. We just use AssImp directly, I think. Yeah. Let's though, I'm not sure if we should have like per format or we should just have a generic thing. Well, for now, let's do func load model. Right, and let's take a file and let's return. So it's called asig. Right, that's the package name. So asig.scene. So when you load anything in AssImp, it gives you a scene, and the scene contains everything you need. So let's do very simple code. So luckily, AssImp is actually very simple. Most of what you need is just in one function, import file. So we give file. Post-processing, it has a lot of post-processing, which it can do, which is amazing. So let's say post-process. What do we want? So maybe, let's see. Oh, we can actually force it to embed textures. That's nice. We can generate normals if they are not already there, but we can optimize. Let's make sure we triangulate. So make sure everything is triangle, because in your 3D program, it might not be a triangle, right? So we need to make sure it's always triangle, and then we can add more things. So we can say asig.optimize meshes. Why not? Might combine vertices, that are being shared instead of having them separate. I think this has it separate some places. I'm not sure. Maybe not. But yeah, it could be that the vertices are duplicated in some places. Doesn't seem. I don't see any of this. Yeah, maybe not here, but it could be. So I guess it might optimize that. Then what we get is a scene. That's what we work with. That's the Golang object. And then a release function. And that is explained in the README, but essentially, the release function releases the underlying C++ resources. So after you import, you might want to do additional things on the imported scene. You might want to extract some specific information. So you need to make more calls to AssImp. And in that case, you need the C++ resources to still exist. But once you are done, you're happy with what you have in Golang, you can release it. And then you only have the Golang data. We don't need the C++ data. So we can free that memory. So this thing we can call at the end. And then an error of any. So I guess in this case, we don't know what people want to use. So we're going to return all of these. Func. We might maybe change it. Honestly, it's a very small function. Let's see. And an error, right? Then in this case, there is nothing else happening. I'm not sure if it makes sense to this case do this, but it's just sensing. Okay, why are you complaining? Okay, so this matches exactly. And now, so where we load the models, I think we have a function load models. Wait, load buffers. Yeah. So we won't be doing any of this by hand. We'll be loading everything. So let's do it here. Right, so let's do, or maybe for now, let's just do it on the main function. So in here, let's do resources, or what do we call this package? Models, right? Models.load model, and then we are going to load the same model for now. We might test with an FBX in a bit, why not? So, but let's load this for now, and then we should give people the ability to, yeah, I'm not sure if it makes sense to abstract it. Well, this is okay. This for now, this is okay. Why are you sad though? name and name. Oh, okay. Let's name them then. Scene error. All right. So we load the model. We'll get a scene, a release function, and an error. Then, as usual, we can check the error, right? And if not, then I guess we can crash, panic, failed load model, and then we can give error is error, right? This should be good. Then we can defer a release. In this case, would only be released after we end the game, which doesn't make sense. Yeah, I mean, for now we don't do anything, so we can't think release. We don't need any extra. So we have the scene. Now the scene has this kind of structure where we have some flags which tell you some of the things that happen when loading the scene or the model. Then we have materials, so all the materials that were exported, all the meshes. So if you have more than one meshes in the model, then you can get that, and then textures and all. So we know we have only one model, so let's just loop over the vertices of the first model. So scene dot meshes 0, right? And then each mesh has a bunch of things, including primitive types. So that's like, are we doing triangles or something else in the model? So in this case, for a game, it's always triangles. And then we have which material is this mesh using, right? So the materials are shared. And then we have like animations and whatnot. But what we care about is the faces, the vertices, the normals, and whatnot. So in this case, let's loop over vertices, right? We'll do len. There we go. And maybe let's just print mesh as mesh vertex count is the same, right? And then let's print vi equals, and then we can print the vertex. All right, so we're just printing kind of all the vertices on the terminal to see what's happening. Hey there, Blackjack. Welcome to the stream. So I'm not sure if you know what we're doing, but we're building a game engine in Golang from scratch. Let's make this a string. I think once we have this is going to be really powerful. Like, we're going to be able to do cool things. We'll be able to load any model essentially, no matter how complex, and have it all textured, and with normal data, we're going to be able to do lighting, so we can have lights and whatnot. Oh, you came from the Reddit post. Nice. Welcome to the stream. So now we are okay. So we have 36 vertices. So in this case, the vertices of the cube, because we have a cube, they're duplicated on each end, right? But this is correct, and we can see this looks like actual data. So you're just starting with Go. Do you have programming experience, Jack? Or are you starting with Go? Hey, Mr. Mugami, welcome back. Welcome to the stream. Let's print. Let's see if we got normals. Honestly, I'm not sure. Normals should match. Each vertex has a normal, right? And then UVs, I think, would also match. UV. What do you call it? Faces. Well, faces won't match the number, but well, we also have color sets, which is nice. We can have colors, vertex colors, right? Text cores. Okay. So text cores and we have multiple text coordinates per vertex. So let's just print. Well, I hope this doesn't crash. PHP and Go 1 2 years. Nice. So you're coming from a familiar background to me. I also mainly do, web dev, but I guess my interest is also a lot in these lower level things where we have to care a bit more about performance than just interacting with the database. It's very interesting. All right, let's run this. See, if we get normals. I hope this doesn't crash because there might not be textual coordinates. I don't know if our cube is textual. I don't think so. One way to know. Oh, we got everything. Perfect. That's so cool. This is why it's so nice to be able to load things instead of doing it manually. So we have normals at each vertex. So in this case, the normal is pointing straight up. It's always normalized. And sometimes, so this is in the z-axis, I think, kind of mostly in this direction. I don't know, it has a bit of a y component as well, and so on. We have UV coordinates, so that means we can texture this. So, and again, like if you guys just joined, you can, if you're interested in just doing model loading, you can actually use this. Where is it? I think it's here. It's AssImp Go, AssImp-Go. This is our the wrapper I made for AssImp in Go, and it's internally using ggLM. And so right now we already have everything as you can see, GLM vectors. And that should mean that we can give all of this directly to OpenGL and to the buffers immediately. So we can load any model, make a buffer of it, and then load it. I don't know if we could do texturing today. That would be so cool. Maybe not. So let's see. So new buffer object, and then we're generating. We're putting these vertices and the indices, right? Which is the faces. I think in here. So let's just check. Don't want the vertices, but I do want to see the faces. And each face has an array. Is each face always 3? Not sure. So in here, the faces. Okay, so all the vertices making up the face. 1, 2, 3. So 2 triangles. Why is? No, I think one is normal and whatnot. So yeah, each face is like 3 vertices. So let's do faces. Let's maybe just confirm that let's do face index counts. So let's just take the first face and say, how many indices do you have? Please tell me your secrets. Then I assume if 0, 1, 2, and let's just print, assuming this doesn't crash. So, Mr. Mogami, are you also web dev, or are you doing something else? Oh, we crashed. Out of range 12. Yeah, this looks correct. Yeah. So these are the indices for the vertices, and we are good to go. So that's perfect, and we have everything as an array already. I think is take this, for example, and plug it in here instead of where is this? Load. Well, just take this boy, plug it in here. So we have this. Now our vertices, we're assuming one mesh, so are coming directly from the mesh, but vertices. And why are you not happy? An array of 32. Well, I think we can actually pass hobby dev. Nice. That's cool. Jack, the goal is to build a game engine, and it's not about the game. Like, I'm not building a specific game yet, at least. Maybe in the future, but I wanted to explore like building a full-blown, like, proper game engine, 3D game engine that you can use to build a high-quality game, right? Maybe not AAA, but certainly high quality. And I noticed also that there isn't anything in Go of the level that I wanted. There are a bunch of 2D game engines where people have their own physics systems and whatnot, but I didn't see, like, for example, a 3D game engine with physics and like a full-blown thing that is generic and can be used by people. And so it's a combined thing where I want to learn about everything involved in making a proper game engine and build something in Golang, right? And I don't think I'll do any scripting language. I think Go is really, really nice, like, to work with. It's simple and gives you a lot of power. So both the game engine and the game code is going to be written in Go. If that makes sense. And that's the idea. Now, what I want to do in the near future is that, and I think we're getting there, as soon as we have a few of the fundamental pieces in, even if not super optimized or anything, I want to just build a small game. So now we're getting to model loading, we have UI in and whatnot. So once we have a few more pieces, then I want to kind of use the engine itself to make a game and see how that works. Yeah, exactly. Yeah, okay. It's all either C++ or C, or it's like C#. I don't know about Java, but like, you know, C#, Java is the same, but everyone's like doing C#. Unity is doing C#. I think there's a plugin for Unreal Engine to use C#. So yeah, there is nothing in the middle, if that makes sense. We want something, maybe it would be interesting to have something a bit more than C, and not the mess that is C++, but less than C#, right? Not as high as C#, and maybe more performant, which Go, to me, certainly fits. It doesn't have all the features. Like, you know, we would love to have control over inlining, for example. But it's also, maybe it's a crazy idea, but if this project gets big enough, then we might even be able to have some say, like, you know, give suggestions to the Go team to implement some features that would be useful in these use cases. Because I think so far Go has focused a ton on web dev, and it's really good for that, but there hasn't been a focus more on, you know, things like this, which are closer to the metal, more high performance requirements, so on. So maybe it could be a use case that they would be interested in supporting. Right. So back to this, we're doing gem buffers, but our nice gem buffer takes a float 32 array, which we don't have. We have vertices, which are, each fig3 is a float 32, but they're not flattened. I am not sure. Although all a vec3 is, and this is not a pointer, all a vec3 is an array. So I think we can maybe just give all of this as a float 32. I'm not sure. At least in some other languages, I think you could. We can try. or we can just flatten it for now, just convert it to FLO32, XYZ, and plug it in here. I am not sure. Oh, for now, let's flatten it. Let's do flatten like 3, which takes 3's array and gives us back a FLO32 array. And then our out, let's say floats, is FLO32 array, and we know the size. The size of the output is the size of the input multiplied by 3. That is more efficient than doing it kind of, keep appending to it without knowing things. Keeps resizing the array, and there's a ton of copies. Not very efficient. All right. So then, since we already have the size, we can immediately say it's vectors I.x. And then we advance by 3. So plus equals 3. Plus 1, plus 2. This is y, and this is z, and then we just return loads. And if my code is correct, we should be able to in here. So let's say flatten this, please. Yeah, so now we have some data coming in straight from AssImp being loaded. The other thing we need is the indices. I'm not sure. Let's see how we'll handle these. How do they come in? So the indices, tangents, vertices, normals. I think they're just the faces, and then each face gives us a Win32. Well, let's just say flatten face. We should think about how to make this interface better, but let's see. So faces are coming in as what? It's an ASIC face. Okay, so it's its own data structure, and the face is, yeah, it's the same as flattening a vector essentially. It's the data structure, but it's just an array internally. So let's do ASIC face faces, and then I think for us a face is always 3, but notes, we are assuming face is always 3 indices. That should be okay. So for each face, you have indices 0, 0, 1, 2. Here you int 2. This is 32. You int. Right. Now why are you sad? Okay, it's just a unit. Okay. Now, all the indices. And then we can flatten faces. Well, let's say this thing. Cool. So now we have this, and we don't need any of this. Don't need this. Don't need this. I hope nothing breaks. One way to know. We run and see. Right. So in load buffers, we plop all of this, then everything is good. Let's see. One thing I should start working on soon is honestly physics wrappers, because that's another thing, again, that I didn't find online for Go. There isn't like a physics wrapper. I have no idea why Go is so behind in this. Okay, this is almost the shape we want, but not exactly. Not exactly. So we kind of have the shape, but in the middle there is a missing face. Yeah, this is basically a missing face right there. Or maybe two triangles. Let's see. But it's almost, it's almost there. Maybe we should have a look at the faces. Let's do that. Just print them. Then, so for the mesh, what are the faces? It could be the optimization also doing something weird, but I guess we'll see. So face I dot indices 0 and 2 and 2, and then just loop j, sorry, 9 indices. This is actually j. So we're printing this face with index j, and then at the end let's have an empty print line just to separate. Let us see. Oops. Now as we do graphics, I think we're progressing really well. Like for basically a few hours of work, all of this is really good. Sound is one thing that I have not explored. Should be very interesting to see. Okay, so 3, 3, 3, 3, 3. Yeah, so they're all 3. And we seem to have the correct number of vertices. We're just kind of increasing. Okay. So why are you then displaying this? Let's disable any optimization for now. Let's see. And we could compare with our old model as well. That did not do anything. This is weird. It doesn't seem 3D. It's like a cutout. It's like a 2D object. Yeah, it has no depth. So if we come back here, let's bring this back and comment like this. This was commented out as well. Right. So you have vertices. At this we don't care about. We load the model, where we have vertices and indices, and then we put them, which we did here, right? 32 gen buffer, and oh, this looks good. Okay, let's just confirm. Because I remember there was a depth. It's like a cube just stretched out. There should be depth to it. So if we get close, yep, there is definitely depth. So that is also going away for some reason. Are we not drawing the whole thing? Okay. 36 seems right. That's the number of vertices we did see. Okay. Let's go back. Here it go. 5, 6. What are we pointing out? The indices. So the indices are these 420. The ones we loaded were all like 1, 2, 3, 4. Okay, yes. Again, let's bring this back. Let's check the code here. So we have faces. This face, these indices 0 and 2, XYZ, XYZ. This seems okay. This seems correct. Okay, and then we print the faces. We can see faces count is ln of this, and then our index count is 3 times that. 3, and this is, we might be simply not drawing the backside, or like all the indices. Come on. 36 indices. All faces. Yeah. This is what we have. 36. Exactly. This is odd. 0, 1, 2, and so on. What we don't apply? So this doesn't work, then we can cross-check kind of the vertices being loaded. The vertices should be the same from our loader and this loader. The indices are very weird. Okay. So yeah, this didn't help. So then let's load it again with our loader, and yeah, let's just print the indices and print this one. It's very weird. It's cut out. There isn't anything in the back. So only the front side is coming. All right. So these are the indices being loaded by AssImp, and this is the one our loader is doing. 420-273. This is not it. It's just going in order. Am I printing something wrong? Nope. This is the actual index. Is AssImp doing something wrong? Maybe. You know what I want to try? We load the vertices from AssImp, but we use these indices. Let's just see. Let's put them here. They might not match, but let's just see if this does anything. Because the ordering seems wrong. Maybe AssImp is actually wrong. Could be a bug. Could be a bug. Yep. No, actually no. We at least see the complete front face and we see something from the top, but the back is completely not there. All right, so this is an indices problem. And the indices should come out in something like this. You know, the order shouldn't be just sequentials, as if we're just counting things. So let's look at Mr. AssImp and see if we have a bug. Mesh. So AssImp go, parse node, parse meshes. Let's do parse meshes, right? Vertices, normals, okay, faces. We have faces, and then for each face, we parse units. How many indices? And then we send the indices. Oh, this looks fine. That's very weird. Are we using AssImp wrong? We are not. Yeah. The uints we're creating are just the uints from AssImp itself. Okay. I guess it's time to look AssImp indices. Edward sees on. OJ format transfer single index buffer, one vertex. I don't get this. Face. So we have the faces, and each face has a bunch of indices. Yeah, it does seem like join identical. We don't get this. Yeah, indexes, push. All right, so we could try. I'm not sure if FBX would help, because people seem to be talking about OBJ only. But this is essentially what we're doing. So the indices coming in are coming sequentially for some reason, or they shouldn't. So in here is like index 5, so vertex 5, vertex 3, vertex 1. This makes up one triangle, right? This makes up one triangle. Now we only have this many vertices. Yeah, only like 8. So the vertices are joined. Now what AssImp is doing is kind of expanding those. Let's try to join identical vertices. That should return us back to 8. That shouldn't honestly matter, but let's just do this. So let's say vertex count, how many are we getting, sir? Scenes, meshes, 0. Vertices. Let's see this. Let us see. And I did test that day with FBX, and it also loaded, which was really cool. So we can now load anything. Okay. Oh wait, it worked. It's not fully worked. So this side, we have this side. I'm not sure if you noticed, there is like a weird gap here at the top. Yeah, on the right side it's not fully loaded. On the left side it's loaded. But how many? Okay, so we got some of them. They got compressed. We have 24. Wait, we still have 36 indices. Does that make sense? 12 faces. Yeah, 12 faces makes sense. A face is a triangle, and we have a cube. So we have six sides, and each side is made up of 2 triangles. That's that doesn't make sense. Index. These numbers are off. Why? Let's try to use the ones we load again. Yeah, so let's take the faces and the vertices from AssImp. See if this makes a difference. Could be just handling it in a different way. If someone has more experience with AssImp, maybe they could help, but yeah, otherwise we look. Okay, now it's even worse. Yeah, it's just the way we're accessing this, I think it's wrong. 0 and 2, yeah, it's just sequential. Then up to 16, is it? All right, so now it's actually being reused. So you can see the numbering is not, sequential. So like here we have 0, 18, 1, which is good. All right, so it's doing its kind of job in a way. What doesn't make sense is why it's still failing. We have 36 indices. This is what we're doing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 12 into 3, so it's 6. Okay. Yeah, let's look at our friend. He's also using an OBJ file. Faces, each face has an index or a list of indices. Then get the scene. We finish all this. Okay, mesh, normals, indices. Okay. Yeah, but where are you getting the indices from? This is the mesh class, all right, and then they're going to get the indices. Bind. Let's go to the last one. I think he has a code. Hello triangle. SDK. Nope. Where is the code? Well, I guess let's look at let's compare the vertices ourselves. So we know this one is correct. This one is displaying a proper 3D object. So we can print this with the indices. So we have this one. And show this one. the vertices, right? So verts and indices, and also we can compare with the flattened objects, right? And we can also get rid of this, so we don't want any post-processing. Just give us the object as is, and let us see how it goes, right? Then you can say info logger right def asig verts, this, then asig indices, which is this. All right. So now we should see 4 arrays we can compare. Let's get rid of this for loop. And I was also thinking whether to make an editor later on for nMage. Might be nice to have like a GUI editor, so you can use it through a UI, not only as a library. You could see. All right, so the vertices, this is from, these are the vertex positions from AssImp, and a bunch of them are all zeros. Wow. Up to a point, it's all good. Then they're just zeros. The indices are these. Then we have again a lot of zero indices. Now, of course, that's not correct. And we have these vertices coming in from our own loader. This doesn't make sense. 0, 3, 4, 9. Okay, this is correct. Are they out of order? So this thing is in the middle. This thing. So we have 2.2, 1, and 0.3. It could be just a different vertex. Let's see. So where is 0.2 in here? This one, 0.2452, 1, 0.3. All right. So we do have the vertices. And I wonder what these zeros are. That is not good. Then these ones are filling as well. This is potentially, this is the bug we might have been searching for in AssImp itself. So in get vertices, this is a one-to-one thing. X, Y, Z. 6, okay. I am not sure. Into 3. Are we flattening it wrong by any chance? Okay, let's print the actual objects. Let's not run any of our functions. Reduce the chance of our own code being broken. Let's see what this. Let's have some new lines. Once we have this working and normals, then we can get some lights in. Lights would be really nice. Instead of this darkness, you can have a ground and some proper illumination. Okay, let's look at this. All right, so it seems our flattening was wrong because I don't see any zeros. Yeah, there are no zeros here. It's all good. These are the verts. This is each vertex. And then all the indices are proper. and then this one. Okay, so our flattening is wrong. That's so stupid. This is an easy function. You should not have gotten it wrong. But does anyone have any idea how this is, why this is wrong? So we send vertices. Each vec3 is just 3 floats. So we make room for 3. How many vertices? Multiply by 3, and then 0, 1, 2, plus 3. Each time we get x, y, z. This is 0, 1, 2. This is okay. What's happening, people? I'm missing something. Probably something stupid. Let's have a look. But yeah, this looks completely correct. All right, I think it's time to debug. Debug, Mr. Debug. Okay. X, Y, Z, floats, float. All right, let's put the debug point here. Let's see. Come on. Come on, VS Code, come on. Oh, this takes so. Is it compiling something from scratch or? Yeah, that's great. But let's look ourselves. How is this? We have n vertices. Each one is 3 values, and then we're just putting them. We're not skipping anything. Oh, right. We increment 1 vertex at a time. We were skipping vertices. Oh my god, yes. Each vertex goes into 3 slots, but we were skipping plus 3. We're skipping 3 vertices at a time instead of skipping 3 floats at a time. So what should happen? Simply multiply by just have, yeah, like we need to multiply by I, and this is supposed to be easy. Okay, so I 3 0, right? And here, okay. So at index 0, at vertex 0, we are going to fill positions 0, 1, and 2. And then at the first vertex, we're going to be, because I is going to be 1, we're going to start at position 3, and then 4, and then 5. This looks correct. And same thing, these faces, where you should only increment 1 face at a time, but each loop we increment 3 indices forward. So you have 2 iterators kind of going on simultaneously. All right. Now we use these buffers, and thus this should actually give us loading. I hope. One of the things, maybe I leave it. I'm not sure, but maybe until we at least do 1 game. Okay, now it's completely gone. At least something is so abstractly rendered, because we might want to use like Vulkan or something in the future. So that should be abstract. But yeah, okay. So this, it's supposed to be +1, 0 +1, 2, 0, 1, 2. I think compilation now takes 12 seconds every time we run. Ooh, finally. Perfect. This is perfect. You can see the depth is there. Everything's working nicely. Amazing. So this is, ladies and gentlemen, is completely loaded using AssImp. We don't need any of this now. Goodbye. So much let's code. We don't need this. In this case, we're not doing anything, so we just release. But yeah. And this doesn't make sense to me. Like, we might as well just use AssImp here. So, right, just that, and then we don't need this anymore. We don't need this whole thing. Bye-bye. Yeah. So we load it directly. Now we can pass some post-processing. Post-process, join identical vertices for sure. And then what do we want? Post-process, maybe, I don't know, gen normals, if there aren't. Sure, and optimize the mesh. This should make no difference to the rendering, but it should reduce the number of vertices that we have to deal with. Less memory, more efficient. Come on. There we go. And yep, perfect. So still a 3D model. Everything is looking good. Now that we have this, we might quickly, we're already like to the second hour, 1 hour. We can pass maybe colors or normals. We want to do lighting. Okay. Well, I don't think this model has colors. Obj doesn't support colors. Let's go to Blender, our friend. Maybe export to FBX. Should load all the same. Right, bye light. So I have a cube. Let's keep it a normal cube for now. Let's see what do we want to do. So I'm not an expert Blender user, but there's a way. Edit vertex paint. Alright, and I just want to kind of color the cube. Let's go into rendering mode. And how do I? Okay, let's say I want to have it kind of a yellow golden color. Why are you not? You guys know Blender. Anyone can help. Draw, mix, radius, strength, brush, texture. I don't want texture. I just want you to do set vertex colors. Yeah, just want to set direct vertex coloring. That's it. Oh, did it paint? What happened here? Oh, okay. Yeah. So these are vertex colors. What one is this? Viewport shading. Viewport shading. Really the same. Anyway, so you can see that because this information is only per vertex, between this vertex and the other one, just like when we set way back when we set the colors directly, it's interpolated automatically for the actual pixels in between the vertices. So if I color this vertex as well, you get this. I can't really color in the middle because there is no vertex here, but I can color this thing, for example. So let's go back, maybe this, and let's put all our vertices to this kind of color, right? Full strength, bottom as well. And then if we export to a format that does support it, something like FBX I think is pretty standard nowadays. Games, very popular. should support vertex colors, and then we can load this into the buffer, and just like before, we can pass it into the shader. Right, so let's export as FBX, right, and let's put it into the desktop. What do we do? We have, well, not AssImp go. Let's go into nMage, and let's put it into resources, models, and we say color FBX. Export. Thank you very much. Let's go back to the code, and there it is. So it's a binary format. You don't see anything. It's not nice like obj. And for now, let's just literally change this. But FBX, that should be it. We should still see, this is Blender. We should still see, we should now see the cube, but we didn't need to change any code. And that's the beauty of AssImp. It just loads a billion formats and parses everything for you. Okay, now on. Look into it. Oh no. What is happening? Okay, so we kind of we have a sampling of a cube. Something that kind of looks like cube, but it's not exactly a cube. But yeah. Right. Again, we're missing a bunch of triangles. Are we doing anything weird? Don't think so. What if we don't process anything? Does that make a difference? I don't. If we loaded one, shouldn't have affected the other. We can check how big each index is as well. While we're at it, print line text count is, let's say, A0 A6. Wait, it's still loading? No, it's there. Yeah. Completely nicely broken. Let's run, get our index count. And once we have that fixed, hopefully, we can start accepting and using the colors, which come into the vertex shader as vertex colors. We set them to the out variable, and then it's sent to the fragment shader, and here we can use it. Right now we're not using it. Yeah, but we can start. Okay, 4 indices per face. What? How is that even? How does that make sense? Oh, okay. Let's make sure we triangulate. Let's absolutely make sure to always do that. Yeah, I think you can tell Blender when exporting to triangulate. I think so, somewhere. Geometry, normals only. I'm not sure, but yeah, I'm pretty sure you can tell it to, yeah, and we have kind of the OpenGL format. Z is forward, -Z is forward, and then Y is up. Yeah, I'm not sure. This is odd. Oh, there it is. That's all we had to do, is just make sure we triangulate to get the 3 vertices. Perfect. Then one thing we can do to ensure this doesn't happen in the future is in here, we can check, kind of make an assert. And it would be nice to have kind of a debug mode only thing. But if you're not used to this, asserts are essentially a way of making sure a condition is met it's like a check that otherwise potentially, crashes your program. And the way, like the reason is, when you're developing, you really want to make sure that some mistakes are not made. Something like this, which is potentially hard to debug. We weren't already dealing with meshes and whatnot. But these checks are removed when you build for release mode, because obviously it's additional overhead. You don't want to, we're releasing it to people. You don't want to keep these things in. So yeah, I mean, Go doesn't have them. In C, it would be something like assert, that, maybe faces.indices. This is our assert in this case. We want to assert, we want to make sure that this is equal to 3, always. If it's not, then you forgot to triangulate, you're in some kind of trouble. But when we are in release mode, we don't want to have this because we don't want to do additional checks. One way to do this in Go is by these flags where you can include. So when you compile Go, you can tell it, hey, here is a build tag. It's called tags. And then at the top of the file, you can have a tag saying, hey, only use this file when the tag is X. It's like release mode or debug mode. So in this case, let's do something simple. Now, you can say if it's not equal to 3, then what we want to do is an error logger, just panic completely and say, what do you call it? Indices space doesn't have 3 indices. Index count is this thing, and we have this, right? And this would crash the program, but give us an idea, like, hey, something really wrong that should never happen. And that should be okay. Now for tags, we can just check. It would be nice to have maybe an assert library in Go. Not sure if there is. Assert Go. Assertions. Testify. Testing tools. Yeah, we want something that is not in testing code, but in actual like production code, but that gets removed at build time when you're building for something else. Go tags. Right. Golang tags. Nope, not this. Let's do build. Yeah, build tags. I think this is a less known feature for you who are interested in knowing more about Go. This comes to like hash defines, bound defines in like C or C++, where we can just disable or enable parts of the code or maybe entire files by having things. So what is this? Yeah, there it is. This thing. Thank you very much. So let's say we have a package. Let's add a new package, right? Let's call it, I don't know, constants, maybe const. I'm not sure. Maybe the name is potentially bad, but let's say. Okay, so let's say build tags. Go. Let's call them build flags, and let's say these flags are for build flags debug. Let's just say debug flags underscore debug. And this is const, right? The difference is we're going to put a tag. Yeah, this is a new way of writing it. So what's the tag? So we only want to include this file when, let's say, we have the debug tag when we build. And I'll show you guys how to do this in a minute. Now, we want another thing, release, and this is kind of this is the default where nothing happens. So let's say, so we have this const package, right? And it's all a bunch of constants. So we want a const saying, I don't know, I want to call, but say debug, right? And so that's it. There's nothing special here. We just want to get some information at build time about the state of our code. And so we say, okay, this is true. In this case, the same consts are available, but the release mode is going to be false. Right? This is going to be false. Now, in the normal case, when we just go build, this is going to be this is going to be included. This file is going to be included. This file is not going to be included because we said only include this file when it's debug, right? And this other file, we can say include this only when it's not debug. And I think that's how you write it. So debug, because otherwise it will be like an error. How can you have a variable defined duplicate like twice? So we say either this file is included when it's debug or this file. They cannot be both there at the same time. And what this gives us is in places like this. So let's say, let's break this check. Let's say if it is equal to 3, we will hit it, which is obviously wrong, but we want to fire the assert. If I build this, go run. This should crash, saying that, oh, you know, the indices are not correct. Come on, my friend. You can do it. There we go. So we crashed and it's complaining, and we say we crashed at 207, and we have this error message saying, hey, your face does not have 3 indices. It's actually 3. So we hit an assert in some cases. We only want to do this if it's debug. So let's say I'll add another check. If const the debug, only then do you do this check. Otherwise, just don't do anything. Right? So will this hit now? Let's see. This now should not hit because we don't have the debug flag, the debug tag, build tag set. And so that file won't be used. Debug is actually going to be false now. There we go. So we run. Even though the indices are wrong and probably there's something broken in the back or something, but or no, actually our indices are right, but like we didn't hit this thing. Because if we look at debug, it's telling us, hey, it's false. It's going to take us to this file. Now let's say when we build, I don't remember how to set the tag. When we build, okay, just tags, go on. Dash tags. So we say, hey, we're building in debug mode. I hope this is the right syntax. Then you go. Running in debug mode, we should crash now. There we go, we crashed, right? So this, in this case, because we set the tag debug, and you can set multiple tags, this file was put in our build. This file was not, because we put a not. So it's either or. Either this one is building, either debug false is there, or debug is there, right? Debug true is there. Only one of them. So since we built with this if statement is essentially if true, and the compiler is because it's known at build time, this is a const, it's known at build time, this is true. Compiler is just going to get rid of this if statement, and we are just left with this thing. And so this check is happening. This is our debug mode. A release mode, debug is false, and so this if statement essentially if false never happens, and so the compiler completely gets rid of this code as if it's never even there, right? As if it's not even there. And so it gives us the ability to have additional checks wherever we want without impacting runtime performance. I mean, this could be doing even heavy things or whatever, or maybe it's just a hot code path that happens a lot, and you don't want extra if statements in there slowing down your performance. Well, we don't have to worry, because when we build, we're going to build, we're not going to set the debug tag, and these things won't happen. So yeah, so these are like Go tags 101. You can put like ands, I think, you just do and whatnot. You can do all kinds of things. It's a very nice, cool thing in Go. No packages found. Yeah, sure, whatever. This is there, this is not there. Yeah, right. So let's put an assert package. So let's do asserts. I would like this to be easier to use, not just asserts dot something. Assert, well, whatever. Asserts, go. So we're just going to kind of package this kind of check instead of having it in a billion places. And asserts, and maybe asserts dot bool. I'm not sure if that's a good name, but or let's say assert true, assert true, and you just get check true. Right, that's it. And in here, what we're going to do, we're going to maybe a check and a message if things do explode, and that's it. This is our code. We're going to say, hey, are we in debug mode? Because asserts should be removed completely from the code if you're in release mode, right? So the way we're going to do this is the asserts are functions, but they always have a check, and I usually don't like to indent my stuff too much. So if it's not debug, I'm just going to return. I'm just worried the compiler won't understand what this is doing. To be safe, let's put it like this. If it's debug, only then do this. So we say if it's debug and the check is true and the check is not true. So assert is like making sure. So if we assert true, then we are saying make sure this is true. So we're going to fail it if it's not true. Right? So if debug is false, this will never run, and it's basically an empty function. Compiler is going to get rid of it. Otherwise, it is not stay. Okay, it's there. If it's not true, as we expect it to be, we expect it to be true, then we can just printf the message. That's it. That is it. Then we can assert false. And what we want is make sure if it's this and it's true, but we expect it to be false. So print panic line, I guess, message, and here as well. And that's all we have to do. So in here we can just do asserts the true, assert that, confirm for us that this the number of indices is always 3, otherwise we did something very wrong. And if it is, then you can do we call it sprintf. Here is the message to show if we did well, right? That's it. I think it's a very nice thing. We might even extract this as a package for people to use, but that's it. So we assert that this is true. If it's true, everything is good. If it's not true, then we have a problem and we want you to crash the program. So in this case, since everything is good, it's equal to 3. When we run with the debug tag, even though the assert is still there, we should, what do you call it? Should not crash, right? Indices are correct. The assert is being done, but it's not failing, and so the game runs. We have our nice cube, green color, But of course, now if the check, no, it's equal to 0, which is wrong. So this should fail. But now, if even though it should fail, if we're not passing the debug tag, it will still run the game. The game will still run because this thing has been completely removed by the compiler, essentially. So we shouldn't at least get any performance penalty. There we go. So this is very nice and important. So we should assert that indices are 3. Well, one thing I guess we could do at the top is check if faces are not 0, but that doesn't make sense. Yeah, that's okay. In vec3 we don't have anything to assert. That's fine. All right, so this is great. Now let's look into colors. So what we should be getting now, since if you remember, we had our nice green cube, but we're not using these colors now in the fragment shader. So we want to pass these. So let's look at where we get our colors. Color sets. What's the color set? Okay. All right. So I think, I'm not sure, but I think this is because each vertex can have more than one color set to it. That's why AssImp has a maximum of 8. In this case, we only have 1. That's what we care about. And then a color is RGBA, so it's a vec4, right? So what we can do is flatten vec4. We should honestly have a place for these functions. Vec4, vec4s. The difference is now this is multiplied by 4. Here we have a W. Well, yeah, so it's a W, which is RGBA. And then here it's multiplied by 4, and this is plus 3. Right. Yeah, that's it. Now let's make a function, another one, vec4. We pass these. It's a static thing. It's a color buffer, right? And the type is a vec4. That's it, I hope. Now, if everything is going well with this loading, then we should be able, in the fragment shader, so the vertex shader is sending us a color. So we get the vertex color, it's sending it out to the fragment shader. We can just use it. In our case, we are hard coding the object color to this. Instead of this thing, we should use the out color, which is a confusing name. It's the out from the vertex shader, but it's the input to the fragment shader. So this is the color of our object. So the object itself has a color, and then multiplied by the light color and so on, and the strength, right, of the light color. So yeah, so it's okay. So if the colors are different, I think it will mix them. Essentially, we're mixing the colors. If we have a colored object and a white light, then we just get the whatever the color of the object is. But let's see if this runs. Okay, so let's do. But we're getting a red. Why is this red? Why is this red? I am putting a white ambient light, but we're seeing a red object. We're seeing a red object in all cases. Wow. That's not expected. Well, I guess we are passing something to the we're passing something to the fragment shader. That's not what we expect. Oh, okay. So ambient color starts at this. Start at 111. Is white. And in here, just to match the UI, ambient color should start at 101. Essentially. Data, right? Or we can just use the nice little GLM, but new, but 3. Wait, why is this a big 3? It should be a big 4. Actually, it's fine. Big 3. Yeah, so new big 3. It's all white. All are maxed. So this now matches our starting value here, and multiply by the out color. So we should check if our thing is even, we're even getting these colors. So in here, let's do printf colors, and what we want to do is scene the meshes, mesh 0, color set 0, and let's see what we get. It's really exciting, starting from nothing and then building slowly to the point where we're loading things, we are getting colors and some lights, UI. It's very cool when we have everything. All right, so we do seem to be having correct colors. So all the vertices you can see is RGB and A, the last component. They are all because we colored the whole thing the same. So they all have the same values, and then an alpha value of 1. Looks right. Yeah, this looks fine. Is there a place we need to pass them? Are we enabling the attribute for color? Ooh, we're not. All right, we need to do this. We need the color buffer. Otherwise, this thing has no value. Word color, is it called word color? Yep. All right, so enabling this. And now, interestingly, after all this, I still don't see that there is a big need for generics, which is going to do, but there might be later. There we go. We have our color. This is so cool. So this is the color we got from Blender. Right? This is without any lights. We're here essentially shining a bright light on it. Right? Blender is more like this. We have this cube. So we're getting the color, and then we're shining a bright white light on it. We have this. Now, if we shine, for example, a red light, get it's going away. Is this correct? I'm not sure. It's like green. Yeah, but it's pretty cool. So we have lights. So we're sending now vertex colors, vertex positions. What we also need is vert normal. Right? We have normals coming in, and potentially you want the normal to be passed to the fragment shader, so you can use it to do lighting. Outcolor is just a horrible name. Any suggestions? We can say vert out, frag in, or just vert color, yes. And then same thing for so this is our vert color, and this is our vert normal. And just like, by the way, the color is interpolated, right, between two vertices. Even a pixel in the middle gets kind of its color is smoothly interpolated, changed between the two values. The normals are actually also interpolated automatically. So the normal is like we actually should do, let's just talk about normals and the basics of lighting, even if we don't do it today. If we have a surface, so let's say this is our ground, right? This is like a flat surface, like a ground. Maybe, I don't know, there's a person. There's a person here, right, standing. The normal of the surface is whatever, like the direction that's 90 degrees perpendicular to the surface. So this is the normal. So in this case, the normal might be as a vex3. It's a 0, 1, 0. It's always normalized. The magnitude of the normal is always 1. Now, if the surface is rotated, so let's say it's like a slant, so the normal is going to be something like this. Right, now, why is this useful? Why do we send even all of its data to each vertex? The reason is it's really useful. One of the things it's useful for is lighting. So if you have, what you can do, let's say we have a circle. We have a nice, and I can't draw straight lines for some reason. We have the sun, right? No, that's not the sun. You know, we have some light in the game. Maybe it's the sun, and it's basically, if we imagine the light coming from the center of the sun to this object, how do we shade it? So obviously the places here are going to be bright because they're facing the sun, and this section right here on the back is going to be completely dark. There is no light coming here at all. And so the way we represent this, at least I don't know about physically based rendering nowadays, but you know, the traditional way so far is with each vertex representing the circle, you have a normal. So you have a normal coming in here, right? This is our normal of the surface. We can compare the kind of the direction of the light and our normal, and you can see if we're kind of in front of the light, then in this case we're going to be pointing opposite, right? And the direction can be, you can flip it, whatever, but it's going to be opposite like this, right? What about this normal? So on the other side of the sphere is going to have a completely different normal in the opposite direction. And we can see, hey, is the normal, according to how much the normal is aligned with the light, is going to get a stronger effect from the light. So a normal that's here is kind of halfway. So that's the thing that's receiving the least light. And if you go anywhere further back, you're not getting any light. We can say this thing is looking away from the light, it's not receiving anything. So we'll pass all these normals, and then we have what we'll do is we'll also pass positions of lights in the game. At least that's the basic way. I'm pretty sure there are, you know, to handle a lot of lights, but the most basic thing is you pass a bunch of lights. You say to the shader, like, here is the position of the light, here is your normal, and then you can calculate using the dot product. It's a very simple calculation if you're not used to it. If this normal is like 1, 0, 0, and then you have the direction, the selector representing this direction, let's say n2 is like 5, 4, 3 or something, then you just multiply, then the dot product is just x1 multiplied by x2 plus y1 multiplied by y2, and the same thing with the z-axis. And the interesting thing about this is it turns out if, and I hope I remember this correctly, if the vectors are pointing in the same direction, the dot product is equal to 1. Right? And I hope I'm not flipping this, but yeah, something like this. If they're pointing in the same direction, it's equal to 1. As they move away, so let's say one is like this and the other is slightly rotated. So as they diverge, your dot product is going to be, you know, maybe in this case 0.8. And then when they become when they become perpendicular like this, your dot product becomes 0, right? And then if they are completely out of sync, one is up, one is down, your dot product becomes -1. So using this, I think we can start seeing how we can take the position of the light, or the direction, right, where, like from us to the right, and our own normal, get the dot product, and we can say, hey, yeah, assuming the direction of the light is coming like this, and this is where the pixel is. If we're in the negative range, if we're less than 0, then we have light coming in from this direction. If we're above 0, if the dot product is above 0, then we're not facing the light, then we should not illuminate. We should not take the light's power into consideration. We should not affect our own color by the light, right? And if you're doing the calculation the other way around, if you just reverse this vector, then it becomes as if you're going from here to the right. It doesn't matter. Then you can just check from 0 to 1 is allowed, and anything below 0 is ignored, right? So it doesn't matter. You can calculate the direction from here to here, or from here to here, but the idea is the same. We just want to check the dot product and see where we are. All right. So I hope this made sense. If you guys have questions, please ask. But this is kind of the theory of what we're going to use this for. Now, first, let's simply vert normal. Okay, so these should match. So the names here should match the names here, actually. Vert color. Okay, so let's call them maybe vert pos in, and same thing. Vert color becomes vert color in, right? And then this normal becomes vert normal in. Then what we send is just vert color, vert normal. Yeah, so vert color equals vert color in, and vert normal is vert normal in, just so that the names actually make sense in the fragment shader. Just vert color, vert normal makes a lot of sense, I think. And what do we say? What do you call it? So we have like 15 minutes. So let's try to get this to work. So let's send the normals now. So if we go, normals are nothing special. You can create a new buffer for them. It's a vec3, just normals. It's a bunch of vec3s for each vertex, and it's buff type. Okay, so we don't have buffer type yet for this. So we can call it vert type normal. So just normals. Yeah, I don't like this class much. We really need to rework the buffers, but for now it's okay. So color and vert position is GL type array. Yeah, same thing. So normals are also just an array in GL. It's also faulty. So all of these end up as GL type array. It's okay. Vert position, why do we use it? Just to make sure. Okay, so you have all these buffers. We want now a normal buffer, like that, right? And say buff type normal, and we are going to fill the normal buffer, right? So anywhere else where we need to change these? Doesn't seem so. Here and here and here, only 3 places. and then data type. All right, so this seems okay. I hope. We have our normals. It's a victory, nothing special, just a bunch of victories. Now we are presenting them. We need to enable this. Oh, so it's called vertical in vertical in, and similarly enable vertex add-ons. Right. And then it's verts normal in. And this makes I hope this makes sense to you guys. Yeah, so this is the normal buffer. We're setting the values, and that's it, I think. That should compile. Now what we can do is to have some lights. I think we can just pass a like, let's say, a uniform for a light 0, and then we can detect the position. So we have this, everything's fine, nothing's wrong. So if it's white, get the position, the color of the object. Okay, perfect. Let's look at our friend, the restaurant. So let's look into lights a bit, just basic lighting. Yeah, so we have ambient light, we did last time. Now what we want is diffuse, and diffuse is essentially what I was, what we just explained on the board regarding the normals and all that. So ambient light is very simple. Diffuse, that's exactly the theory. We just have a light position, we have normal. Yep, we have normals coming in. Okay, so we have, right, yeah, so they're doing the same idea. I think nowadays we have more advanced stuff, but we can start with this, wrong with that. So with the uniforms is light position 1, let's say, in case we have multiple lights. And then we're calculating. So what he's doing, we have fragment position, which is just the model matrix. Okay, so he's transforming into world space, right, by multiplying by the model matrix to get where the fragment is. They're doing it from I think this is also interpolated in world space. Yeah, okay, is this also interpolated? I guess so. This is also being interpolated. Yeah, and then we get the light direction, which is this arrow we drew from the light. And then they do the dot product and so on, and we just multiply. Right. The normal vectors to world space. Normal matrix. Okay, that's fine. Can do it later. All right, so let's try to do this essentially. Let's take this code. So in our vertex shader, we have a light position coming in, and fragment position. So frag was model into this. Why do I bracket here? Right. Right. Okay, this looks good. Why are you sad? There's something wrong. Model. Oh, model mat. Okay. Model mat. That's that. So we have now where our pixel is. Fragment is like the pixels. And then need this coming in fragment position. Okay. Then uniform will be available in both places. Don't think we need it here. We just need it here. Right, that position. High positions, we do this, send the normal, which we did, fragment position, and then this is kind of our calculation. In our case, we don't need to normalize. I don't know why this is being done. It should already be normalized. Basically, I'll have a magnitude of 1. Yeah, I mean, we expect them to be normalized. We can check, but I don't think we need this. Light direction. So we are subtracting our fragment position from light position number 1. So in this kind of subtraction, so it doesn't matter if it's like which way it is, except for the, you either will have a minus sign or not. But the thing here is where the vector is pointing. So since we put light position minus fragment position, the direction arrow is like this. So the head points to wherever the this position is, to the left of the minus sign. So we get this kind of arrow. And so in this case, if we face the light, then our two normals are parallel. And that means our dot product should be between 0 for this case. And if it's like, if it's a normal here, then it's going to be 90 degrees. Sorry, from 1, dot product is 1 for this case where the angle is 0, up to an angle of 90 degrees where the dot product is 0. The dot product is below that, like here. The dot product, if the normal is here, then the dot product is going to be less than 0. So we can ignore it. This is essentially. So we have the direction to the light, and now we can take the dot product from our normal to the light direction, which is happening right here. And I'll explain its code. It's actually, straightforward. So let's do it one step at a time. So in this case, we have, float dot, it's called light dot, right? So we have our normal, which is the vertex normal. This thing, why are you complaining? Why are you sad? Syntax error. What? Semicolon, comma, victory. I don't get you. Oh, it's in, not it. All right. So we dot product the light direction and this, and since the direction is going like this from the pixel to the light, so if we are facing the light, then it's going to be either from 0 to 1. The dot product should be from 0 to 1. So if it's from 0 to 1, we want to use it. If it's less than 0, we don't want to have negative light, whatever that means. If the dot product is less than 0, let's say it's a completely opposite arrow, then we want to completely ignore the light, so 0 it out. And this is what the max is doing here. So this number is going to be between -1 and 1. Right? And so we only care about the range from 0 to 1. Otherwise, we want a range like this. We only want 0 to 1, nothing else. So we are going to say, hey, please pick the max between 0 and this number. If it's above 0, then just take this. If it's not, then give a 0. Don't give me anything below 0, because if it's like -1, so 0 is going to be higher, and we'll use that. Right? And this is essentially what this calculation is doing. Is you can shorten this essentially to just put this here, and that's it. This is a normal vector. This is a normal vector, basically magnitude 1, and then we get the diffuse strength. So this is really diffuse strength. How strong is this light affecting us, affecting our color? Is it shining straight on? Is it the strongest, or a bit weaker? And then we also need what is the light color. So light color one. Right? Just like we have ambient light and its strength and color, we also have light position and color and the strength we calculate using the position, right? And this is what they do, right? They have light color. Where is this? Yeah, so they just have light color, and then we multiply this. So ambient, so they're adding them. I'm not sure about adding. I'm not sure. We can add and then combine. Okay. Okay. So now we just have to finish this up. All right. So let's have a vectory. Final ambient color is this thing, right? Then we're going to multiply this by final time plus the light color one. Add them, multiply them, and we have our fragment color. Now that we did this, what do we have? Do we have a new in? No, this is not normal in. Nope, we just have a new out. But we have 2 new uniforms. So let's think about our object. Let's put maybe the light at let's say 111, right? Because our cube is starting in the center, so let's actually put it at 2. Cube is size 1. Let's put it at 2 to have it a bit away from everything. So yeah, in here, guys, let's do var light. What do you want? Light pose 1. Which what? GLM vectory equals so let's position it at 2 2 2. Actually just up, right, and up. Let's keep it in the center, so no Z in this case. Then we don't need a strength, but we do need light color. So light color 1, right? And in this case, since it's color, let's use a vectory, right? Same thing, vectory, and let's start it at just white. Okay. And then where do we set the uniforms? Set uni. There we go. So this is okay. So the main function. Lights. So let's do simple shader. Set uniform break 3, and the first one is this thing. Is light position 1. That is light pos 1, and we have light color 1. Just maybe today we can see something. We can see colors. We can have lighting, some basic lighting at least. Right. So color and this. I don't think there's anything else. Is there? Well, I guess let's run and see. We should make it controllable from the UI, but let's see. Just maybe. If it really works on the first run. Oh, we have white. It's really white. Okay. All right. So I think it's working, because before, when we remove the ambient light, nothing shows up. But now, because we have a different light shining on, even if we remove completely the ambient color, we still see what we had before, which is when we made the ambient light max, right? And we saw this bright green cube. It's amazing, and the ambient light has no effect. But because we are adding the two together, increasing the ambient light fully, it's like too much white light coming in. Perfect. So it does seem to work. Although let's have it controllable in the UI. This is why I wanted the UI, right? It makes it really nice to use things. All right. So similar to this one, right? So we have light plus 1. Light, why did you die here? Come on, can do it. Come on, go. I think it's correct. Right, final. So then the color as well. Lights, color 1. Position, color, light color 1. And then we have lights. Now position is not between 0 and 1, it's between, let's say, 0 and 10. Right? Let's say 0 and 10. I think that's it. Let's run and maybe get rid of this huge metaf. Yeah. Okay. We should get used to running with a debug tag. Make sure our asserts are there. But yeah, it's really cool. I am happy we got to this stage. Using AssImp is definitely changing things. All right, so we're starting at a good, correct position. Let's reduce, let's disable the light color 1. This is not supposed to be. Oh, okay, we're using two things moving together. Light color 1. Oh, okay. So this thing is light color 1, the data, light position, color, ambient. All right, perfect. Let's run the debug tags. You guys have suggestions for what to do next? Anyone excited about something particular we can look into? All right, let's disable. Exactly. So we have our light, and we completely shut it off, basically, it's 0. So the only thing affecting is the ambient light. So it's all white and it's giving us a strong kind of green color. So if we halve it, so we have this. This is what it looks like in Blender, right? Just a dull green. Now if we add on top of this, and if we go completely off, it's gone. Now if we start adding light, it's this. But the thing is, the normals don't seem right, because we should see, now that the ambient is gone, we should see the light kind of shining from one direction, not this. Yeah, you know, not. I mean, maybe we do need to normalize diffuse. Oh, are we not? Oh, we're not multiplying diffuse strength by, yeah, diffuse strength by the color. Now it's correct. But the light position, the normal, so the normal doesn't seem right. Maybe we do need to normalize it. I'm not sure why. Normalize. Let's see. I would like to see, you know, something that's properly shaded. Then maybe next time we can look into textures. That would be cool. Okay. Right, so now it's kind of confusing to look at, but yeah, we have some different colors. Let's disable ambient light. Okay, perfect. So we have shine light, light shining from kind of the left. Let's move it. Nice. So we have light that's moving. Now the light is at the top, so let's move it up. So the light is now high up, and kind of. I don't think. Are we moving the camera and not the object? Not sure. But yeah, I do expect it to move. But anyway, yeah. So we're moving the light, and you can see how it's affecting different sides of this, and then the sides that are not lit are completely black. Right? Can we move it? Bring it forward. Okay, so the position does need to accept negatives. Position is, let's say, between -10 and 10, and yeah, otherwise it's good. Okay. So now, again, let's disable ambient light completely. So we have a light there, right? And yeah, okay, so I think it's moving. Yeah, we're moving an object. I think so. Does it get brighter or not? Yep, yeah, so the object is moving. It's affected by the light in different positions, in different way. So let's move the light now. Let's put it a bit more high up, centered on the X, and let's bring it forward. Set. We should be seeing a different side, honestly. Okay, yeah, so it's, I don't know why it's looking transparent, but yeah, we have kind of semblance of something, and then if we have a bit of ambient light, we can see that some sides are kind of colored and then the rest are not. We should not change the alpha. I think that's the issue. The alpha is set to 1. Sure. I guess we can check this next time. We don't exactly have this, but I think we're close. Adding, yeah, results is, so we have vertex colors multiplied by this. So we normalized the normal with the light direction, which is already normalized, and then we dot product the direction, and we have the diffuse strength multiplied by the color, and then we add these, which is already this thing, and yeah, this looks okay. I think it's a pretty good starting point. We don't have this, unfortunately, for some reason. I'm confused, but I'm not sure why it's happening. Normal. Yep. Diffuse light color one. Where is he getting his object color from, though? What's the object color? Yeah, it's mixing. It's adding those and then mixing it. Strength. Not sure, honestly. Yeah, yes. Can stop here and push this and end today's turn. Let's try one more time, maybe have a revelation. So the strength is weak ambient light, and let's move the light. Okay, yeah, so we can see the light is pretty high up now, so the top, right? And then now it's illuminating the top and the sides, and then the center, which is in front of us, is dark. That's why we see kind of a weird shape like this. I would like to rotate the camera now, honestly. But yeah, we do need rotation. That's okay. We can do this next. Right, so we have a lot of things. Let's ignore models. Small model, have this. So today's work, I think, is day 8, and we added, let's see, what did we add? AssImp plus yeah, I mean, doesn't completely fog shading yet. Basic lights, and then asserts. Very productive day. So AssImp integration, basic lights, asserts, normals, verts, or say verts, normals, and colors. Right, that's it, everyone. Thanks so much for coming. Guys, need to pull something for coming to today's stream. I hope you enjoyed. We are doing so much work and we're progressing nicely, and I hope you join us next time where we continue to do this, and maybe in a few weeks you can start doing the game, any game. Yeah, if you have ideas, please share it, and enjoy your day.